So this is really kind of the meat. If there's going to be one thing that you take away from this whole talk, there's a few different ideas that I'm going to introduce to you. But the biggest, most important one that I want you to remember is this identity-based segmentation. There's 5 policy checks that should happen at every hop in your infrastructure. And I would argue, and we do in this SP, that if you realize these 5 checks at every hop, you are realizing a zero trust architecture. You're implementing that policy of mitigating access and bounding an attacker in space and time. So what are those 5 policy checks? Nothing crazy, right? The first is encryption in transit. And really the key reason that we have encryption in transit is not, because FIPS requires it, which is true, and different compliance regimes like PCI DSS also require it. But the real purpose there is twofold. One is to prevent eavesdropping. So we don't want somebody who, maybe has physical access to the wire to be able to see the data that's in transit. And 2, message authenticity. We don't want someone to be able to tamper with the message while it's in flight. We want to know that the message that the server received was really the thing that the client sent. And encryption gives us both of those properties, eavesdropping protection and message authenticity. 2, we need to authenticate the services that are communicating, the applications that are communicating. Is it the application that was built by the production system running in production, right? Or is it the running on the developer laptop, right? And 3rd, we need to use that authenticated runtime identity to authorize application to application access. So we have encryption in transit, we have a notion of a service identity, and we use that identity at runtime to make decisions around what applications are allowed to communicate. That is binding an attack in space. The idea is that if an attacker compromises one of our workloads, the space that they are going to be able to pivot to attack is limited by that service authorization policy. That bounds it in space. And the time to live of the credentials and the credential refresh helps bind of the authentication token, helps bind that attack in time. Those aren't enough alone, but they help do both of those things. 4th, we want to authenticate our end user. And ideally, we'd like to do this at every hop. When we can, by the way, get into some of the technical questions here around like how we might do 3 and 5 authorization and how we might do authentication. We can definitely dig into that if people want to ask questions around those. There's some interesting engineering trade-offs there. But regardless, we want to be authenticating our user identity at every hop. For example, one way you might do this is by implementing JOTs. And so an API key comes in the front door. We exchange it for a JOT, a JSON web token that we use internally. And one of the beautiful properties of a JOT is that it is locally authenticatable. I don't need to talk to a remote server to validate, to authenticate that token. So that gives us a good set of engineering trade-offs between availability, but authentication and the ability to bound an attack in time because of token expiry. So there's a bunch of techniques there, but regardless of the way that we do it, we need to authenticate our end user, ideally at every single hop. And then finally, at every single hop, we should be using that end user identity to perform an authorization check. We want to make sure that the workloads that are communicating and the user in session are allowed to do the action on the resource in question at every hop, at every chain, every hop through your infrastructure. If we do those things, we realize the zero trust system. We mitigate the damage that an attacker can do, and we answer that question: how do we bound an attacker in space and in time?